Okay, welcome to part 3 of the VHDL tutorial series. In this part, it's going to be divided into 3 sections. Since sequential logic is a very complex sort of topic, I'm going to keep it very simple. The first section of it is going to be over just flip-flops. And, that's very easy to understand and conceptualize. And then the second part is going to be about counters. And counters are a little bit harder because they introduce incrementing of logic vectors, and that's not really that intuitive because VHDL is very strict when it comes to type conversions, but it's very simple once you get the hang of it. And then the final one is going to be state machines, and that's going to introduce a lot of concepts such as state types and different types of conversion and different language structures, because normally we've just been using whens, selects, and just normal combinational like assignments. Sequential logic normally involves the application of the if case statements and then a whole concept called a process. But I think first of all we need to explain what a process is. So process clock. Apologies. So you've probably seen this before in one of Krim's examples, process whatever, and then you begin. And you probably don't know, what is this talking about, a process clock? Well, a process is, let me explain. So when we're doing combinational logic, I've drilled into your head throughout these past few videos that if you were to write something such as Q is B or something and QB is H, both of these statements or assignments execute at the same time because it's not telling a CPU what to do, it's telling a piece of hardware how to exist. And so this is basically true parallel programming, right? So these and this, so the order of this doesn't matter, they execute at the same time. However, with processes, it brings it back to its roots of a more traditional programming language. Oh wait, I need to identify the ports. So for this first part, we're going to be making a D-type flip-flop, and okay, so here we have the D-type flip-flop. He probably has not gone over this in class. If he has, you know that D-type flip-flops, when it's the rising edge of the clock, well, this is a positive edge triggered D-type flip-flop, and that's normally what you want. So here, if D is 0 and the clock is on the rising edge, Q is 0, Q naught is 1. If D is 1 and the clock is on the rising edge, Q is 1, Q naught is 0. If the clock is not on the rising edges, so if it's on 0, 1, or the falling edge, it doesn't matter what D is going to be because Q and Q naught are going to stay the exact same. And this is very important for all sequential logic because this is a sort of memory circuit that helps you temporarily store information and is very useful for transitioning states and whatnot. So now we have clock is an in standard logic, D is an in standard logic, Q is an out standard logic, and QB, which is going to be, Q bar or Q naught, is an out standard logic. Of course, we do not need that last semicolon because the last semicolon is on the parentheses of the port. All right, so now we have our process clock, and I can finally explain what a process is. So, as I said before, processes use sequential sequential execution, line at a time execution. And the beauty of it is that, especially for very complex state machines, you could have multiple processes going on at the exact same time, and they execute in parallel. So the stuff inside a process does it line at a time, traditional programming, but each process can be executed in tandem with normal combinational assignments and other processes. So let's start. So here we have it, we want to, all right, the rising edge of the clock, Q, and whatnot. So, okay, so the sensitivity list. I should probably write a script for this, but I find it more productive to do it this way. The sensitivity list, all this basically means is that when the identifier of clock changes at all, if it goes from a 0 state to a 1 state or a 1 state to a 0 state, everything within the process is reevaluated. You could technically do combinational logic in processes if you just typed the thing process all, because that works. You can process every single input and output, or I think all just does inputs, because if you did it with outputs, you need to switch it to a buffer, and that's a whole other can of worms that we don't need to talk about at all. But yeah, if you had it within, if you had process all and then you just wrote combinational logic, it would work out just fine. But I don't like doing that. I prefer using processes with sequential statements only, and I just find it's a whole lot easier for me. So yeah, so we can start the clock and then we begin the process. And then here, because we're designing a positive edge triggered D flip-flop, we want it to only execute the code on the rising edge of the clock, never on anything else. So in Crim's examples, you've probably seen something like this. If clock equals 1 and clock event then. All right, you've probably seen that. This is basically saying if clock is 1 and clock is returns true if signal S has had an event this simulation cycle. What that means is that if it's changed, essentially, if it's gone from one value to another, so if it's a 1 and it has changed from a 0 to a 1, then whatever. There is a much better way of doing this. It was a function introduced, I think, in the 1993 revision of this, so I don't know why websites still use this old, antiquated way of doing the rising edge, but you can just do rising underscore edge of clock. And rising edge is, of course, a function which is part of the standard logic 1164 package. So we have it here. So if rising edge of clock, we want, Q to be equal to D. And it is as simple as that. It really is as simple as that. Yeah. Because we're having here, so if the clock is rising, if it starts at 0 and the clock rises and falls and D is still at 0, Q is gonna be 0. But if D switches to 1 and it's not on the rising edge, if the clock goes from a 1 to a 0, it's still gonna go down the lines of code and it's gonna see this if rising edge of clock, and then it's gonna be like, oh, I'm not on the rising edge, so I do absolutely nothing. It's only when the clock changes and it's the rising edge of the clock that it executes the Q is assigned to whatever the value of D is. So then we end the if there, and then we just end process. So, but we need QB, and I believe we can just do QB is 1 when Q is 0, else 0. Because, and the reason I didn't add it here, because you'd say, oh, Alex, how come you can't just do this? How come you can't do that? Because it does it one line at a time. It's going to, if rising edge of clock, then this, and it will only execute that on the Okay, it will only execute the first line for each cycle. It's very weird. That's why you don't want to do multiple assignments under a single if. You want to keep everything that you can have combinational. So we can save this, and then I can demonstrate the simulation of it just really quickly. So let me just stop the recording, and then we'll be back momentarily. Okay, so here we have the simulation I've made of the D-type flip-flops. At the top here, this is an actual D-type flip-flop, and then this is the code that I've created. And here's the thing that toggles D, and then here's the clock. So as we see here, it's at 0, and the clock is pulsing. It remains at 0. So if I switch it to 1, D is going to be 1. But you saw that delay there. It waited until it went from dark green to light green. So I think I can slow this down a little bit to show it better. What? Are you kidding me? I can't do half frequencies? Does this work? That is so stupid. Alright, well, I guess we'll have to cope with with 1 hertz. Jeez. What a severe limitation. Alright, but, so as the clock is pulsing, you saw how it delayed there to change. Just, you put the video on quarter speed and watch what's happening. So yeah, I think that gives you an idea about the D flip-flop. Next, we're going to be moving on to the JK flip-flop. Okay, so for this, I actually had to find this in a different book because the other book didn't have an example of JK flip-flops. So what's going on here is this is, I think, in my opinion, a superior way to do registered logic. Is that you have when J and K is 0, when they're both 0, and the clock is going up, there's no change whatsoever to the outputs. If J is 0 and K is 1 and it's on the rising edge, Q goes to 0 and Q bar goes to 1, so it resets the state. When J is 1 and K is 0 and the clock is going up, it of course sets it, but then when both are high, it's going to toggle it back and forth. So I really think this is it's a better way of setting and resetting memory, in my opinion. I know that there's set and reset D flip-flops, but I just think this is better, in my humble opinion. So let's begin coding it. So we can keep the Q and the QB. So we need a J and a K. So we basically have the exact same concept going on here, but now we have a dilemma. We have multiple inputs, and we have in our process. So we can just do nested if statements. So of course, it's going to value on the rising clock edge. So if J is 0 and K is... we don't even need that because it's supposed to be no change whatsoever. So let's do if J equals 1 and K equals 0, then, and of course we know here we assign Q to be 1. And it's as simple as that. Now we do an else if statement. J is 0 and K is 1, then of course we have it, so Q is 0. It's the, wait, I need semicolons, I'm so silly. All right, now we have a third state that we need to address when they're both 1. So else if J is 1 and K is 1, then we just have Q equals not Q. And it really is just that easy. And we have to add an end if here. So yeah, and this is how you do this sort of thing. If you have multiple conditions that need to be met in a very simple thing, you can do nested if statements. If that, else if, and you don't really need an else because it assumes that if none of the conditions are met, because what's happening here is that it processes through the clock and it's like, oh, I'm on the rising edge. I don't meet this condition, I don't meet this condition, and I don't meet this condition, so I'm just gonna do nothing. And then it ends the if, and then it ends the if, then ends the process, and then evaluates that. Well, not then. It evaluates this at the exact same time it evaluates this one. But yeah. So let's see this in action as a simulation. All right, so right here, of course, just like last time, we have a actual JK flip-flop up here, and then we have our coded version of it. So let's click play. Of course, they're both on 0, and as we have established, if they're both on 0, nothing's changing. So if I switch this and then turn it off, of course, it's staying on 1. So that's nice. And then if I click K on, of course, the next clock pulse, it switches back to 0. And then it's staying here. But if we do both on every rising clock pulse, it's, of course, alternating, just like is described in the book that we looked at, and just like how it is in our code. So this is going to be the wrap-up portion of the very simple, very simple fundamentals of sequential logic, I suppose. And I'm going to be going into part 2. It's going to be in the exact same video, so yeah, just give me a moment and stay tuned for that. All right, so we are now on the second portion of the sequential logic tutorial. This is going to be all about counters, and basically counters are a type of state machine where they don't necessarily need an external input. This is going to be running like forever. You know how a counter works. If you have it stuck in the up, it's going to count in binary from 0 to 15, then loop back to 0 and 15 forever and ever, and it doesn't really need an external output. But for the sake of learning, we're going to be making a down-up counter, sort of like a 74191, but that's not going to have any presets. But in the state machine portion of that, since it's more complex, we're going to be going over that. And of course, this is still going to be using the if statements because that is the most simple way of doing things. So we have a down up as an in standard logic, and since we want to make it a 4-bit counter, we have Q is a out standard logic vector of 3 down to 0. It's making it 4 bits. So here we go. And of course, as previously discussed, we start with a process clock and then begin. So you might be wondering or thinking to yourself, how in the world do we increment a standard logic vector? It's not actual binary. How can you add an integer to a logic vector? Well, that is where this package, the numeric standard, comes into play. So, of course, for our counter, we want it, let's make it so If it's low, it's in the up, and if it's high, it's in the down. So let's begin. So if rising edge of the clock, then so now we can begin properly. So we have it if du equals 0, then. So now you might be thinking, all right, that's fine and dandy, but how do we increment the standard logic vector? You cannot do q is q plus 1. That's a completely illegal statement, and it's going to throw an error with this library. So what we do is type conversion. So if we go here, there are 3 different types of type conversion. There's automatic conversion, which we don't really care about. But what we do care about is typecasting and then type conversion functions. So VHDL is an extremely type-safe language, but you know how in like C++ you can convert integers into like floats and stuff just by declaring it to be an integer. You can do the exact same concept here. That's why you can make something. What this is here is that SLV is defined up here as a standard logic vector. A standard logic vector you can convert unsigned binary into a standard logic vector by just making it a standard logic vector. And this is a type of typecasting. So if we go here, the way we would solve this problem is Q is the standard logic vector of unsigned Q plus 1. And that works because, sorry for that interruption, I had to do something real quick. I forgot what I was saying, so I'll just continue. So here, because standard logic vectors and unsigned is essentially the exact same sort of thing. They're both an array of bits. They can be, as it says in the book, just typecast. So here we have, this is how you would do it normally. If you have an unsigned called unsigned, you can convert it to a standard logic vector by just making it standard logic vector and then put unsigned next to it. So that's what we're doing here. First, we're converting the standard logic vector into unsigned. We're incrementing it by 1, and then we're converting it back to a standard logic vector. So yeah. So that's in the up case, else if du is 1, then q is a standard logic vector unsigned q minus 1. And if. And if. And process. And it won't actually, and because it's a unsigned vector, the way unsigned binary works is that it won't actually, it will overflow essentially. So if you're at 1, 1, 1, 1, and you add 1 more to it, it will overflow, so it will go back to 0. It won't escape the width that you have assigned it here. And this is a very simple case of a counter. Then I will show you how this works. Alright, so this is Alex back here again. A good thing to do with counters is they're a little, the GHDL simulation is a little, how do I say this? It's very particular when it comes to signal assignments. So first I have to make a signal called count, and then I'm going to make it an STD logic vector of 3 down to 0, and then I have to give it an initial value of nothing. And the reason I have to do that is because the way VHDL interprets stuff is that it interprets it as an undefined signal, which is I believe it's an X. So it's not. It has no idea what to actually do when it's simulated. In real life, like if you were to compile this or synthesize this code, it wouldn't display this behavior. But because of the way the simulator works, I have to do this. So count, and then here in the combinational part, I can just assign Q is count. And that should work perfectly fine, I believe. So let's check. Yeah. All right. Yeah, here we go. Now it's counting. Of course, it's counting by binary. It's at 7 here, 8, 9, 10, 11, 12, 13, 14, 15. Then it goes back to 0 because it's overflowing in the unsigned. And of course, if we count down, 2, 1, 0, 15. So that is a very basic counter. It's extremely basic in that it is completely synchronous. You're counting normally. But here, next I'm going to show you a counter that doesn't count normally. It's actually going to be lab 4. It's going to be an asynchronous form of counting. So it's kind of hard to describe, so I'll just show you. Okay. So the example I have for the non-linear counters is going to be lab 4 part 2. And this is a very eloquent solution that I found, and it can actually fit on the 22V10, meaning that if I copy pasted this in the ISP liver and made a JEDEC and put it on a 22V10 and set it up, it would do it. It would do it flawlessly. So the constraints for this, I guess, variant of the lab 4 part 2 is going to be, you either count up or down. If you're counting up, it increments all the way till it displays 19 on the 7-segment display, and then it can't go any higher, and it also turns on an LED. And then, of course, when you put it in the down mode, it will count all the way down to 0, and it won't overflow. Because remember last time, in the last example, it was overflowing from 0 back to 15. So the way I decided to do it is that this implementation will require just the PLD, 2 7-segment decoders, the 7447, and then 2 common anode 7-segment displays. So what we have going on here is that we have a 7 down to 0, so we have 8 bits. The first 4 bits represent the second digit in the 7-segment display, and the last 4, the least significant 4 bits represent the the first digit in the 7-segment display. So you might be wondering, that's a really weird way of doing it. But what I really like about this is that you can hover over something and it will display decimal, hex, and binary for anything, including bit fields. So the way we have to look at this is that I'm using integers here, 16, 25, that might seem very random, but if we hover over it, the integer 16, it will actually display what we want in hex. So that's going to be a 1, 0. So we can divide each 7-segment display, so the least significant digit for the integer is going to be the least significant part of the hexadecimal, and then the most significant is the most significant. So when it's decimal 16 on the 7-segment display, it's actually displaying a 10. So that's why we jump from 9 to 16, because what's going on in the 7-segment display is it's going from 9 to 10. But I'm getting ahead of myself, so let's start from the beginning. In this part of it, I actually use an integer. And I find integers much easier to deal with for nonlinear sorts of things. Really, it's a toss-up between, in the last part we used a standard logic vector, and then we incremented it using typecasting. But here we're using integers. So let me walk you through the process. Of course, I create a signal called count, and it's an integer with an initial value of 0. We process the clock that we begin, and of course, rising edge of clock to make sure nothing else is happening. And then here, if it's in up mode and count, and this is a very good example of using the relational operators. So if down up is 0, so if it's in up mode and count is less than 9, then it's going to increment count by 1. Pretty simple. And then on this else if it's still in up mode, but the count is 9, instead of incrementing by 1, it's just going to jump to 16. So, yeah, it's going to continue just jumping to 16, because what's actually happening on the 7-segment display is that it goes from a 9 to a 1, 0, or a 10. And then here, this is just for if it's in up mode and count is greater than or equal to 16, and count is less than 25, and 25 in hexadecimal is a 1/9, so if it's less than 19, really, then it's going to continue incrementing. And from the lessons we learned with the JK flip-flop, we do not need to have and count equals 25, count is equal to count, because that's implicitly, implied. So yeah, so we have here for the up portion, if it's from 0 to 9, 0 to 8, it's going to be counting up by 1. So when it's, 8, it goes to 9, and now when it's at 9, it evaluates this. If it's in the up thing and the rising edge of the clock occurs, it goes from 9 to 16. Then from here on out, 16, another rising edge of the clock, and it's in up mode. It's going to continue incrementing until then it hits 24. Then it increments it by 1. It's on 25. There's nothing for 25, so it does nothing. And then here, when it's in down mode and the count is greater than 0 and less than or equal to 9, then of course it will decrease by 1 every single time. And if the count, of course, is equal to 16, we want it to jump to 9, because we want it to go from 1, 0 to 9. And then, of course, here, if the count is greater than or equal to 17, and then it's going to be count is count minus 1. So pretty simple with integers. But you might be thinking, well, Alex, the integers, how are we going to convert that to the standard logic vector? Are we going to have to use a crap load of when statements? That's very tedious. Well, no, you don't. So if we scroll down here, we have this thing going on here. Out count is standard logic vector to unsigned count, comma, out count length. What does that mean? So if we go back to here, remember I was talking about there's 3 types. Automatic we don't really need. Typecast is what we did last time. Now we're on the type conversion functions. And then we see here as a table the different types of functions that we need. So if we want to convert an integer into a standard logic vector, we're going to need to do this function. To standard logic vector argument width. Oh, whoops. All right, so actually, I lied because we're not using the unsigned package. First, we have to convert the integer to unsigned, and then we use the type conversion of unsigned, the typecasting of unsigned to standard logic vector. So that's what's going on here. So we begin at the beginning. We start at the end of here. So we're converting the integer to an unsigned binary. And then you might be wondering, what's this outcount parentheses length? That's just a shortcut for writing 8, because it's saying, instead of having to write the integer 8, we're saying we want outcount, the length, the bit width of outcount. So it says returns the number of elements in array A optionally for dimension n. So this is basically, it looks at outcount and is saying, how wide are you? You're 8 wide. So this is just shortcut for writing 8. I like it better because, to be honest, it looks cool. It's nice and red. So now that we've converted the integer into unsigned binary, this is now unsigned. And then we can just typecast it to a standard logic vector and assign it to outcount. It really is that simple. And then, of course, since we wanted the LED to turn on when it was at 19, we have LED out is 1 when count is 25. Otherwise, it's going to be 0. So I've already set up the simulation for it. So let's get it going. So of course it's counting up. And I was too lazy to do the 7-segment decoders and then with 7-segment displays. So I just have it displaying. All right, actually, let me explain it. So this wire up here is the most significant 4 bits. And then the wire down here is the least significant 4 bits. And these are displaying it in decimal. So it's getting the exact same effect you would get if you were to plug these into the two 7447s and then plug that into a 7-segment display. So of course here we have the LED is off because it's not at 19. We're counting 3, 4, 5, 6, 7, 8, 9, 1, 0. Not 10, 1, 0. And then 17, 18, 19, bam, that turns on, and it's not counting up anymore until we put it in down mode. 18, 17, etc., etc. Just wait for it to go. All right. So that's basically it for this thing, and we're just gonna look at this really quick. This is the VHDL equivalent of a 74191, and this is the sort of stuff. It's single process, so we can go over it. All right, so we know that the 74191. In addition to just being a normal 4-bit counter, you also have a preset, a reset, a load, and then we have that ripple carry output, and then the max min thing. So let's start here. So of course, we started out by having the signal count as a standard logic vector 3 down to 0 with an initial value of 0. Oh yeah, we also have an enable. Because of reasons. Oh, because we want the load to be independent of the clock and we want enable to be independent of the clock, we put it in the process. So remember, as we said before, if it's a processing the clock, it only evaluates the process when clock change. But now we have enable and load here, which means that since load is here, if load changes, it reevaluates the process, and it doesn't really care about the clock. And same with enable. So when we begin it, as we know with the 74191 datasheet, if load is low, then it actually does the loading thing. So of course here we have our inputs of clock, the presets, which are the capital A, B, C, D on the 74191, the up, down, enable, and then load, and then we have our 4 bits output, the max, and then the ripple carry output. So down here, if load is 0, then count is preset. It really is that simple. And I've tested this, enable, if it's disabled, it will still load a preset. So if enable is 1, then count becomes Q, essentially. It doesn't change whatsoever. It's whatever the last output was. And that way, if you set it back to 0, it will still resume it. It won't have to restart everything. And now down here, we have if rising edge of clock and enable is 0. Because remember, we only want it to count if enable is, enabled, and it's an active low enable. Then if it's in the count up mode, then of course, what we looked at last time, the standard logic vector is unsigned Q plus 1, which is a type conversion, and I wrote out a very long comment here. And then of course, when it's in the down mode, count is standard logic vector decreased. So that's the end of the process. But then here, if you actually look at the datasheet of a 74191, you notice that RCO transitions from 1 to 0 on basically when the count is 15 and the clock is transitioning from 1 to a 0. So we have it, RCO is 0 when falling edge of clock, and count is 1, 1, 1, 1, else it's a 1. And then we have here, pardon, because max it's only 1 when it's at 15 and doesn't really care about the clock. Max is 1 when count is 15, otherwise it's a 0. And of course, because of the way it is, we have to assign the output to be the signal. And I don't really need to simulate this. You can just go play around with a 74191. It is quite literally the exact same thing. And I've tested this, and it works very well. So yeah, that's kind of it for counters. And next we're going to be getting into state machines, which is significantly more challenging, let's just say. All right. Okay, so for the sake of time, I'm not going to do a code along for this one, but this is a very useful website, HDL bits, for doing hardware description language, but unfortunately, it's in Verilog. But still, it gives very good examples for which you can go by. So for this example here, we have a state machine, and state machines are different in that counters, traditionally, it only really cares about what the current state is, and then it moves on to the next state, because, I'm at state 1, so next I go to state 2. But state machines are significantly more advanced because not only does it depend on the current state, but it can depend on one or more variables, other like inputs. Because remember when we were doing the counters, we had the down up, essentially. That's a very simple Moore state machine. When it's in the count up mode, it goes up, and when it's in the count down mode, it goes down. And it's very simple. But for state machines, it would be each individual state has its own branching outputs. So for here, we have state A, B, C, D. And then we have, depending on the input, if the input is 0 and it's at A, it stays on A, otherwise goes to B. If it's on B and it's 0, it goes to C, otherwise it stays on B. C goes to A and D, and then D goes to C and B. And then it has an actual output where when it's state D, it outputs a 1. Then it also says here that include an asynchronous reset that resets the finite state machine to A. So I've already coded this, so let's go through each individual thing. So first of all, we have our numeric standard. I just like having that, even though we don't add anything. So we have the clock, the switch, which is the input, the asynchronous reset, and then we have the output here. And for the sake of simulation, I have the two testing things here, which I'll get down to when we actually sign it. And then here, because I don't want to write 00011011 every single time, we can define a thing called a constant. So constant A is a standard logic vector with a width of 2 with an initial value of 0, 0. And that's just very shorthand of writing bit fields or whatever. So we have A, B, C, D, of course. And then we have a signal called state and next state. And I like doing for state machines, I usually either use 2 or more processes. And we'll get to that in a sec. And of course, these are representations of the constants A, B, C, D. So we begin, and for the process, we have this thing called the clock behavior. So, of course, it's going to process clock and then the asynchronous reset. So if asynchronous reset is 1, it will jump the state to A independent of the clock. So it doesn't care. It'll just send the state immediately to A. And then otherwise, on the rising edge of the clock, it sets the state to be the next state. So this is more like the state setting behavior. And then down here is what defines what the next state is. So it's going to process the state and then the switch thing. So it only cares about when it switches states and when it switches inputs. So here we use the case statement, which is similar to the C++ switch statement, and I find it to be much more intuitive in VHDL. So you just say case state is. So we're switching the identifier of state. So we're saying when it's A, which is the same thing as saying when 0, 0, then we do a push out. So when A, if switch is 1, then, next state is B. Else switch 0, it stays on A. And the reason we need to actually include the thing where it doesn't change is because state, we're assigning next state to be this. So we don't have something where if we were holding down the asynchronous reset and it stays on A, if we were to put the switch to 1, then switch it back to 0, the next state will still be B because there's nothing in here to redefine the next state. So we need this control statement of switch is equal to 0, then next state is A. And then we do that for the next thing. When B, if it's 0, goes to C. If it's 1, stay. And C, if it's 1, go to D. If it's 0, stay on A. If it's D, if 1, then go to B. If 0, go to C. And then you always need this when others, because as before mentioned with the uninitiated values, if it is on an uninitiated value, it will just automatically set the next state to A. But that doesn't matter since we've already predefined state and next state. And then down here we have the combinational stuff. Of course, here it's saying output is only 1 when state is D. So we have output is 1 when state is D, otherwise it's going to be 0. And then the testing points, test 1 is going to be the state, and then test 2 is going to be the next state. So let's simulate this. I've already built it. So here we have it going here, and as we assume, if it's A and the switch is 0, it stays. So let's hit the thing. Next state is 1. Now the new state is 1. Now, if we let go of this, next state is 2. That's 2. And then the next is 0, etc. And then if we hold this down, we can switch the next state. So it's 1 or 0, 1 or 0. And then when I let go of it, it's here. So there. And then when it hit D, the output turned on. So yeah, that's a very basic state machine. I'll go over a few more advanced ones. But this is pretty simple for... this is really all you really need for the traffic light thing, honestly. Because way I did it when I took this class is that I had you know, you have 10 traffic lights. You have red, yellow, green, and then the turn lanes, yellow, green, yellow, green. 3 plus 3 plus 2 plus 2 is 10. 22 V10, 10 outputs. Yeah. So you would just have like a constant for each thing. Like, I don't know, the constant is the default turning yellow, blah, 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 or whatever. And then you would just use case statements to sort out the traffic light. So, yeah. I believe later I will do some more, and that will be included in this video. But, yeah, I'll see you in the next one.